Hello everyone. In this video, we are going to talk about the required sample size and test power. So one of the things that if you have ever done a test design and you wanted to collect some data from a sample and then come up with some conclusion was, do I even have enough number of, let's say, participants or data in my sample? Is my sample is big enough to draw some valid conclusion out of it? And you might say, well, maybe 20 people is enough, maybe 50 people is enough, maybe not, I need 200 people. So where do you get to mathematically come to a conclusion? That is what we're going to talk about in this video. So remember, one parameter that we talked about in previous videos was significance level, or alpha, which was the probability of making a type 1 error. What was type 1 error, or we call false positive, is when you reject a true null hypothesis. So your hypothesis was correct, but you wrongly rejected it, incorrectly rejected it. That is what we call a type 1 error. And the smaller this alpha is, the better your chance of not doing a type 1 error. Okay? Yes? So that means if something is true, then you are not going to reject it. You are going to accept it. That is a small alpha. On the other hand, we have something called power of a test, or 1 minus beta, which is the probability of correctly rejecting the null hypothesis that was false. So in relation to this power of the test, we can define beta to be the probability of type 2 error, or false negative. What is this? Means this time the null hypothesis was false, but you didn't reject it, you accepted it. So you see, type 2 error is exactly opposite of false type 1 error. Type 1 error, it was true, you rejected it. Type 2 error, it was false, you didn't reject it, you accepted basically. So beta is the chance of that. So clearly, if you want to do a good job, you need to make sure alpha is as small as possible, as well as beta. Both of these type 1 and type 2 error probabilities should be as small as possible. So now 1 minus beta is called the test power, which basically the probability of not doing a type 2 error. Okay? Or correctly rejecting a wrong hypothesis, a false hypothesis. So as I said, small alpha and small beta. Now, small beta means 1 minus beta is as large as possible, as close as possible to 1. So what numbers are desirable for power of a test? Numbers like 80 or 90%. Most of the time, 90% is the power of the test, which means your beta is only 0.1, so your power of the test is 0.9. So if you go with alpha of 0.05, and beta of 0.1 means only 5% chance of type 1 error and only 10% chance of type 2 error. Now, if 10% is too much, again, you can make even this one also to be 5%. And then your power of the test is going to be 95%. So your test has 95% chance or power of rejecting something that is false. If you came up with something false, 95% you are not going to accept it. That is how powerful your test is. Good. So these are the two numbers. Now, you might say, what does it have to do with the number of sample, the sample size that you need to perform a test? I'm going to show you that. If you are doing a two-sided z-test or t-test, for a single mean, so it's a one-way, one-sample t-test or z-test, and two-sided, two-tailed. Okay? So, or for it could be like a pair t-test as well, because pair t-test is also similar to a once or a single mean t-test. So if you're doing a pair t-test, if you're doing a two-sided z-test or t-test or anything, as long as it's two-sided and as long as there is a single mean, whether z or t, the number of data you need comes from this formula. Z of 1 minus alpha over 2 and Z of 1 minus beta, sum of these two Z added together divided by this guy here, which is what we call the effect size, okay? And then square the whole thing and then round it to the closest integer number, okay, to the next biggest number. So this formula is for any one simple, once or single or one way or single mean test, whether T or Z, as long as it's two-sided. So clearly, to calculate this number, you need to decide your alpha and beta. So I need to know what my significance level is and what my power of the test is. Also, I need to know the standard deviation of the population, and I need to know delta. What is delta? Delta is what we call the minimum detectable difference, or MDD, okay, which is basically the minimum size, the minimum difference between the two groups, or the mean of the group and the mean of the population, that you want to be able to detect. What is it exactly? I'm gonna tell you with one clear example, okay? So this is the minimum detectable difference, or MDD. If you know that, or you decide on that, and you know sigma and you know alpha and beta, so you look at Z tables and get these numbers, then this formula exactly is going to give you the number of samples. Now, before we look at the example, let me just mention something. If the test that you do is still two-sided, but this time it is for an independent or two mean group, two mean test, as opposed to one, so it's not pre-post, it's just two different independent groups, then the number that you need is 2 times that, okay? And you might say, where are the proof for these formulas? The goal here is to show you how to apply these formulas, not how to prove these formulas. If you want, I can add some references in the description of the video and tell you where to find these formulas, the proof for them, okay? So here my goal is just to show you how to find the number of data in the sample, right? The required sample size. But again, we can always add some references if you're curious about the proof of that. So now that we know, based on the one single mean or two independent groups, what kind of formula to use, let's look at one example together. So let's say here you are testing a new heat treatment on some metal. In this case, this aluminum, 660 T6 aluminum. The goal of you is to increase the yield strength of this material. From the past data, you know that for a single sample standard deviation, the sigma was about 10 megapascal. Now here you decide that the minimum meaningful improvement in the yield strength is 5 megapascal. In other words, if the improvement in the yield strength by your heat treatment is less than 5, to you, it's not even meaningful. So here you see that minimum detectable difference, MDD, here you decide on that number. You decide that, hey, any change in this parameter, in this case yield strength, below this number is not even meaningful to me. If all I can do is add the strength of it 2 megapascal or 1 megapascal, to me, it's not really even worth it. It's not meaningful. So here you see delta is something that I pick in this case. And Now you want to do a two-sided test, two-tailed test with an alpha of 0.5 and a test power of 80%. You want to know how many samples you need to test if you do a one sample, if you want to do a paired test, or if you want to do two independent samples. Okay? So one time you do a paired t-test, the other time you do a two independent t-test, and you want to know for each one of them what kind of number of samples is that you need. So scenario one, let's say it's a paired t-test. So what you need is go to your z table and one time find z of 1 minus alpha over 2. Why alpha over 2? Because it is a two-way test, right? It's a two-tailed test. So you have to use alpha over 2. And 1 minus alpha over 2, in this case z of 0.975. If you find it, you see it's about 1.96 from the z tables. Also, since your power of the test is 80%, you go and look at z of 0.8 and you see the number is 0.842. And now you're going to add these two numbers together, which is going to be about 2.8. The minimum meaningful change is 5. The standard deviation is 10. So this parameter, delta over sigma, which, as I said, it has a name and we call it the effect size. And effect size is basically a measure of how large the true difference is compared to the standard deviation. Okay, so you divide it by this effect size. So that's another terminology that you learn. So you divide the sum of these two z's divided by the effect size, and you're going to square it up. So the effect size is 0.5, sum of those is 2.8, divide the square it, you're going to get 3139 minimum number of samples. Now, number of samples is an integer number, so you have to round it to the next number. You have to use basically a ceiling operator. And so the minimum number of samples that you need to perform this test is 32. So you need at least 32 samples to achieve 80% power test, or 20% chance of type 2 error and 5% chance of type 1 error. Okay? Yeah? And now if you have two separate samples, then you need to multiply that by a 2. So this time, each group needs 62.79, which if you round it, you need 63 per group. But you have two groups, so you have to multiply that by a 2. So this time you need 126 specimens. Break it into two groups of 63, and now you can basically get the same power of the test and get the same significance level, or alpha. Now in MATLAB, if you want to find the number of samples that you need, there is a command for it. The command is called samp size power. So what would you need to give to it? The first one is sigma. The sigma in the denominator, okay, this one. Then you need to give it delta, the minimum detectable difference. Then you need to give it power, which is 1 minus beta. And then you need to give it alpha. And guess what? It is going to return for you the number of samples. So this is if you want to not go and read all of the z's from the z tables and then calculate it yourself. This single command does all of that for you. Now, going back to this example, let's look at some of the important things that you can get out of this formula, okay? So we need to go and look back at this formula and draw some very important conclusions. What are they? First thing is, if you want to keep the same significance level and the same effect size, so you don't want to change this term, you don't want to change this term. if you have bigger sample size, n goes up, that means this 1 minus beta is going to go up, right? So more power means beta is like, I don't know, 0.05, 0.01, and 1 minus beta is like 0.95, 0.99, as opposed to like here 80%. So when 1 minus beta gets closer and closer to 1 and the chance of type 2 error drops, that means, of course, when this number goes off, the z number for it, z at 1 minus beta, also goes up. So when this term here goes up, of course, the n goes up and vice versa. So I can say that if I want a bigger power of the test, I need bigger samples. Or I say if I use bigger sample size, then my power of the test is going to go up. That means the chance of doing a type 2 error is going to go down. So I'm not going to have false negatives. I'm not going to accept the wrong hypothesis. I am going to reject them. Okay? Yes, so bigger samples always help with that. So that's the first thing that you can see. What else can you see? Now, if you want to reduce the alpha, so if you want smaller alpha, what does a smaller alpha mean? Smaller alpha means a smaller chance of doing a type 1 error or a false positive. If you want a smaller alpha, that means, so alpha goes down, that means this number 1 minus alpha over 2, this guy is going to go up. When that number goes up, the z at that is also going to go up. So if you keep everything else the same, which is the power of the test and the size effect, when the chance of type 1 error goes down, which means z of it goes up, that of course needs a bigger sample size as well. So you see that if you want better results, or basically smaller chance of type 1 error or smaller chance of type 2 error, both of them means you need bigger sample size. Okay, do you see that? So more accurate tests, smaller mistakes is always the result of a bigger sample size. Bigger sample size make our results a lot better. What else can come in? The next thing is this effect size, or SE, or size effect. That is this guy in the denominator. So this could be a function of sigma or delta. So let's say sigma is constant. Let's say sigma, based on all the data I have from the past, that's constant. So this is now clearly going to be the effect of this delta, minimum detectable size. What happens to this? The smaller this delta is, the denominator goes smaller, the whole thing goes bigger, n goes bigger. So you see, smaller delta means bigger sample size. So if I want to detect significance, even for very small changes, I need to have more data. So here, if I say, hey, instead of saying, well, any change below 5 is not meaningful, if I say, well, to me, even a change below 2 units is meaningful. So I say my delta is 2 instead of 5. To me, any change above 2 is also good, not just above 5. Even anything above 2, I would call it some moderate change, and I still accept it. Then what's going to happen in this formula? This is going to be 2 over 10. This is going to be 0.2. And if you change this guy to 0.2, this guy is going to be 2.5 times bigger. And when you square that 2.5 times, it is going to be 2.5 times 2.5. So this number will be divided by 6.25. It is going to be like 6.25 times bigger. So now instead of 32 samples, you're looking at something like 190 to 200 samples. Do you see that? So the smaller the difference that we want to call significance, in an inversely proportional to the square of it, we need bigger sample size. Okay, so I hope that you can see the effect of them in this formula. So if I want to draw some conclusions for you based on these results, the first thing is really try to increase the MDD if you really care about large improvements. So do not care too much about the small improvements if you cannot afford to have lots of samples, right? Do not do that if you cannot make enough of samples. Or in other words, if you have enough of samples, that's fine. You can always detect smaller and smaller meaningful changes. But if you don't, try to come up with a reasonable minimum detectable difference. So try to use as big as MDD that is possible, as big as delta as possible, to keep the number of samples down. The other thing is paired designs are more powerful. Why? Because we just found that if you have a paired test or study, here the number behind this squared is 1, but if it's not paired, if it's 2 independent thing, now you have a 2 per group, and since you have 2 groups, you also have to multiply it by another 2. So you're literally looking at 4 times more samples. So if you can do a paired test or a paired t-test, for instance, it's much better than to do independent t-test. It is going to reduce it by typically a factor of 4. The question is, can you do that? That is the main thing. Now, in this example, if we go back and look at the example, can I do a paired t-test? Well, it depends on how you measure the tensile strength, okay? Or the yield strength. If the way to measure the yield strength is not a destructive method, so the specimen that you used before the heat treatment, you can again use it after the heat treatment and get the yield strength, then yes, you can do it. But most of the time, you know that the test we do to get a yield strength, like a tensile test, we are going to deform the material beyond its elastic point, and the material cannot be recovered and turned back to whatever it was originally. So once you apply the test on the material, you have to throw it away and come up with a new specimen. So if your test is destructive, guess what? You have to use a 2 sample t-test, and that is exactly what you have to do here. So in this case, if I want to be realistic, my number is this one, it is not this guy. Okay, because the way I do my tensile test is typically a destructive test. So if you can do it, that's great. If you cannot do it, then you have to go with whatever you have. Good. The next thing is reduce sigma if possible, because you clearly see that when sigma is reduced, look at the formula, when sigma is going to go down, the whole denominator goes up, so the whole thing goes down, n goes down. So a smaller sigma means a smaller number of samples, and it's kind of obvious because when you have a smaller sigma, it means your data are much closer to their center. They are clustered about the center much better, or we call it the measurements data are tighter in terms of their spread. So if I can cut sigma by a factor of 2, that means the number of samples I need is going to go down by a factor of 4. Now, how can I make sigma possibly smaller? Well, for that, I need to make sure my measurements are tighter. In other words, my measurements are more accurate and more precise, especially more precise. They can repeat the same thing over and over. It's not like if I did a test on one specimen, first time I get 100, next time I get 200, next time I get 50, right? But if I can repeat the same thing on the same specimen, one time I get 100, next time 101, next time 99, right? Close numbers. That means the spread of data is small. That means I need a lot less samples. So if you can have more homogeneous samples and more precise measurement methods, okay, if I can do that, that of course needs a lot less samples. But of course, it's costly, right? Because getting more homogeneous samples means your machine should be, and your operation should have a lot less tolerance, and your measuring devices should be more accurate. So this is a costly option. Means your manufacturing is costly, but your quality control can take advantage of that. Here, again, it depends on whether your measurements are destructive or not. This one depends on how much you care about to call significance or not. And the last one is one-sided test versus two-sided test. All of these formulas that I showed you, both of these formulas that I showed you, they were for two-sided test, if you look. The difference between them was whether it's one sample or two sample study. But both of them, if you look at both of these, they were both two-sided tests, right? You can see it here and you can see it here. Now your question is, if I want to do a study that is one-sided, it's a right-sided or left tail or right tail, what do I do? The only difference, as you know, instead of 1 minus alpha over 2, use 1 minus alpha. So this guy is going to be this. And how does it change? Well, if alpha was 0.05 instead of z at 0.975, I use the one at 0.95, and you know, it is going to go down a little bit, right? Z at this number is less than Z at this number. So what you will do is this number is going to go down a little bit. And for that reason, the whole N is going to go down. Okay? So a one-sided test will require a smaller number of samples compared to a two-sided. Okay? And as I said, it will slightly reduce N. It's not a big thing because Z, again, of 0.95 and 975 are close to each other. So the most critical factor, I would say, is if you want to keep the same power of the test and the same significance thing, the most important thing to do is really either first, if you can do a pair test so that 2 does not exist and it's a 1. The other thing is either reduce this by caring about only larger differences, or try to use better manufacturing and measurement tools and bring this guy down or make this guy up. Okay, so these are the ways to control the number of samples that you need and the meaning of test power, the meaning of effect size, and the meaning of minimum detectable difference, or MDD. So hopefully this video was useful to you. You learned something, and I'm going to see you in the next video. Thank you.